Hello?
Yes.
Are you recording this?
I just started.
আচ্ছা আচ্ছা হ্যাঁ হ্যাঁ সেটাই সেটাই
Thank you. So yeah, the particle is moving back and forth. So it's traveling from surface 1 to surface 2. Before it collided with the surface 2, it had an initial velocity of cx, considering rightwards right as positive. And as it was going backwards after the perfect elastic collision, the speed remained same, but the velocity did reversed. So that's why we have a after velocity of minus cx. Now have a read for this phrase. Between two collisions with side 2, the gas particle covers 2L distance. Between two collisions with side 2 means what? If the particle starts from here, I mean, let's say the particle goes up over here and eventually comes back. So by covering a total amount of distance of 2L, it's gonna collide with the surface 2 once, or with the surface 1 once. We are assuming that the length is one part and the collision that happens afterwards. So this is a key part, that between two collisions with side 2, the gas particle covers 2L distance, which means that if I put it in a different way, let's say the particle starts from surface 1 and then it hits surface 2 and reaches up to surface 1. Reaches up to surface 1 doesn't mean that it doesn't essentially yet collided with the surface 1. It's about to collide surface 1. So for one collision with the surface 2, the total amount of length that the particle has to cover is 2L. Or if you consider from here to the left, either way, I mean, here we have only mentioned with side 2. We could have also written that's for side 1 as well. That also works. That from one collision to the next collision with the same surface, how much distance that does the particle have to cover? Try to figure that out. Colliding with surface 2 and then once again colliding with the surface 2 once again, reaching all the way to the left and coming all the way right to the right. How much distance does this particle has to cover? That's what I wanted to ask.
2L.
That has to be 12. Exactly. That's what is written over here. That between two collisions with side 2 or side 1 for that matters, the gas particle covers 2L distance. So the time that requires between two collisions is distance over time, distance over speed. So that is be 12 by x. So এই এক্সপ্রেশনটা বুঝা গেছে কিনা দেখো everyone. Speed equals to distance over time, so time equals to distance over speed, or equals to 12 by cx. So therefore we get the force that will be delta b by t, rate of change of momentum, equals to minus 2mcx divided by time, which is 12 by cx. So we get minus mcx squared divided by L.
So cx টা কোথা থেকে আসছে?
Delta p হচ্ছে momentum, cx is the speed of the particle.
Oh, acha.
Because we are considering this alignment as a horizon, as an x-axis, that another perpendicular side as y-axis, the other perpendicular side as z-axis. So just to represent the velocity of the particle in this case is considered to be exclusively along the horizontal axis, not in y or z. We have used the subscript x.
Oh, okay, thank you.
Sure. So we replace the value of delta p over here and we replace the value of time over here. So we get force equals to delta p over t. So we have this expression. So that is minus mcx squared divided by L, which is the total force one particle will collide between two collision. Now have a look. In the container, the particles actually move in all directions. Since all particles are identical, statistically we can say cx equals to cy equals to cz. Now this is the generalized, one of the generalization that you understand. That if the particle, if I mean you have a certain number of particles, which would be n, capital N, which will show up in a bit. You have a certain number of particles which are trapped within this container. They are not essentially going anywhere, or they are not escaping out of the container. No particles are entering into the container from the outside, which means at any point their resultant velocity is 0, which brings you the idea that because the particles are moving in a three-dimensional space, I can pretty much assume, for the sake of homogeneity, that all the individual components, average component velocity for all the particles would be exactly equal, because the particles have the same magnitude of velocity in any direction that it moves around. For average velocity, if in any direction it moves around for at a constant temperature. And because the container was described to be a cubic container, so the amount of time it would require to collide between these two surfaces would be the same for these two surfaces, or would be the same for these two surfaces as well. That's why we are assuming that these three components should be equal. Now, these are the three components on the YZ axis, X, Y, and Z axis. And if we write in the vector sum, by vector idea, that that total resultant should be equals to Cx vector plus Cy vector plus Cz vector. So this is a vector equation. That's why we have only used the summation sign. But this summation does not mean numerical summation. This summation means vector summation. And if you just work for the magnitude of those vector components, you might as well write by Pythagorean law that C square, which is mean, equals to Cx square plus Cy square plus Cz square. That's just from the idea of a Pythagorean triangle, two set of triangle, to be honest. Now, for those of you who do not understand this part, I'm going to show you one thing so that it makes better sense to you. Just hold up a second. This is a nice one. Okay. Try and have a look over here. They have given different dimensions over here so that we can talk about these lengths very easily. Can everybody see this figure?
Yes, sir.
Yes, sir.
What I need you to understand that ABCD is the horizontal bottom base of this cuboid. This, what is this color? Maroon or red?
It's pink.
I guess.
It's not pink.
Just say red, sir.
There is a bit of an ash color mixed in this pink.
Red, light red. It's more like light red.
Okay, let's call it red. No big deal. So this red triangle is essentially a right angle triangle, although it doesn't appear to be a right angle triangle because we are trying to represent a three-dimensional object in a two-dimensional piece of paper or your computer screen or my computer screen. That's why this angle appears to be an acute angle. But in actual scenario, this angle is not an acute angle. How much is this angle? For example, the angle HEF. How much is this angle?
90 degrees.
It is supposed to be 90 degrees. And similarly, EHG, this angle, which is appearing to be an obtuse angle, is also supposed to be 90 degrees. The reason they are appearing to be slightly distorted because we are trying to represent a three-dimensional body in a two-dimensional surface. So we are trying to give us, so we are trying to represent the sense of depth by sort of tilting the figure. So what is happening over here? You can see over here there is a right angle symbol. So this red triangle is flat with the base of the object. So this right angle triangle is on the surface ABCD. So this is the right angle of the right angle triangle. These are the two sides, 5 centimeter and 2 centimeter. So we can very easily find out the diagonal. We can find the hypotenuse, that is AC. This would be 5 square plus 2 square. So AC square would be equals to 5 square plus 2 square. Do you understand this part?
Yes, sir.
And then there is this green triangle. This green right angle triangle is actually a right angle triangle that passes diagonally through the object to the other corner. So it starts with a single sharp point on the left side, left bottom corner, which is A, and this is the other edge, and the base is AC. So this is the triangle that actually goes diagonally through the cuboid onto the other side. So this triangle ACG is a right angle triangle that is inside and angled inside the cuboid. This is not visible from a surface. They have shown us this thing, this triangle, so that we can visualize where this triangle is located. So the three vertices of this triangle is A, G, and C. G is on the diagonally opposite corner, C is on the diagonally opposite corner, and A is over here. So AC is what we call a surface diagonal, and AG is what we call a three-dimensional diagonal, or just diagonal for a cuboid. So diagonal for a cuboid means passing through the object to the exact opposite corner, and surface diagonal would mean on any of the surface. So AC is a surface diagonal, AG is an actual diagonal. So this one produces another right angle triangle. And for this right angle triangle, I can say AG square equals to GC square plus AC square. দেখো এটা বুঝা যাচ্ছে কিনা? Where this angle ACG should also be a 90 degree. Now, considering this information, if I just go ahead and try to manipulate this in our figure, so I can pretty well write over here that at the beginning I wrote that I said that AC square should be equals to AB square plus BC square, and then I said AG square should be equals to AC square plus GC square. Now, if I just replace the AC square over here, I might as well write that AG squared equals to AB square plus BC square plus GC square. দেখো এই জিনিসটা বুঝা যাচ্ছে কিনা?
স্যার এটা কি ভেক্টর ওই 3D ভেক্টর
3 dimensional, হ্যাঁ। বলবান এই জিনিসটা একটু দেখতে থাকো। I'll need a small washroom break. Okay, I'm back. So this is the case for the diagonal thing for our scenario. So what we are trying to show up for this ideal gas particle velocity component is something like this. I would like to zoom on it. Let's say for a certain particle, let's say this is a cube, not essentially a cube, but I used an example for a cubed to make sense of the lengths much too easily. So let's say the C actually is working along this direction. So I'm going to use a blue arrow, no big deal. So let's say the actual velocity C is working along this direction. So let's say this is our C altogether. So I'm labeled this as C. So this part, this one should be CX. Let's say this part, let me label with brown. This part is, let's say, CY. And let's say this vertical part is CZ. So now you can see it very well that if you do want to find out the value of C, you can very well you can write this whole thing that C square equals to CX square plus CY square plus CZ square. So that essentially transcends from this large equation that I wrote a bit earlier, right over here. So this is possible us to achieve. So using that, I'm going to take all of your questions. Just keep your hands raised and give me a bit of a time. So using this idea, we are writing this equation. And because we just said a little bit earlier that statistically we can consider all the components equal. So we're going to replace this thing over here. So we have replaced CY by CX. We have also replaced CZ by the same component. And as a result, we now have 3CX square. So we can write CX square is equal to 1/3 of C square. This is the RMS. This is the MS velocity, mean square velocity. This is not root mean square because we have a square inside. So this is what we call the mean square velocity. So CX square can be written as equals to 1/3 mean square velocity. We're going to replace this CX square in this equation to get the force. So we're going to do that over here. What is that remaining part? Oh, here is that remaining part. Oh, acha. I actually messed up 2 pages. Is there a way I can reorder this? I don't think so. This is supposed to be below this one. This is supposed to be above. বললাম বুঝছো কি বলছি? ওই যে দেখো পিছনের পেজে কিউব দেখা যায়। So after this one, we are supposed to have this page. Okay. So have a look over here. We are replacing the value of CX square over here. So force exerted by one particle with one collision is m into 1/3 C square divided by L. So we just replaced this CX square cx square over here. So in place of cx square, we wrote 1/3 mean square velocity. That is for one particle. If we have n number of particles, they're gonna produce n collisions within the same amount of time, and the total amount of force exerted by n particles on the surface 2 would be given by this much. And if we want to find out the pressure exerted by n particles, pressure is defined as force per area. So pressure will be given by n particles. S লেখা আছে because whenever you become this n, this one should become plural. That's why this Adnan Sami wrote another s over here. So this is not a variable name. This is just particles s, grammatical s. So pressure exerted by n particles equals to F by A, which means pressure equals to this whole thing divided by L square. Now pressure is a tensor, so minus sign is omitted. Now tensor, do you guys understand what a tensor is?
Scalar quantity.
A tensor is essentially I'm not totally completely clear with the idea of tensor, so I should not be going in deep into this discussion, but I can tell you what I do understand. That scalar quantities has magnitude, that's one property, and vector quantities has direction. So vector quantities has a tensor value of 1. But there are certain other properties, other quantities which depends on the direction property, which is less or more than 1. Whenever that happens, those things are defined as tensors. So all vectors are also a tensor where their tensor value is 1. So that direction dependency can also have a sort of magnitude effect towards it. Oops. So the direction information can also have a quantity of the direction attached to it somehow. I'm not quite sure how, I cannot explain this properly, but what I know this part is that pressure is a tensor. So because pressure is a tensor, we have omitted the minus sign over here. So that's just a simple information that you need to remember. It is never going to be asked in your question that why this minus sign was removed. I removed the minus sign, but if you bear with me, one thing I can also tell you that this minus sign would not have been in our equation if we did consider in this figure towards left as positive in the first place. So the minus sign would not actually matter. So we got rid of the minus sign so that the minus sign doesn't pop in our equation. So we did this. So this force divided by the L square gives us the pressure, and then we do the calculation. Ultimately, we get 1/3 mn c square, and L cube become volume. So if we do the cross multiplication, ultimately we get tensor something that takes in a vector and gives out the value, and thus the sign is omitted. Yeah, it's something like that, shown of what you just wrote me, but I cannot explain this properly to its full understanding. That's why I'm not trying to get into that whole thing. Plus, it's not essential for a syllabus. That's another reason that I can skip the discussion. But thank you for the information. So PV equals to 1/3 mc square. So we are getting this equation over here, and this is one of the primary equation, one of the key equation we're going to be using through a lot of our mathematical operation for this chapter. So all of this whole thing that we just discussed through, these were relevant for the discussion of PV equals, for the derivation of PV equals to 1/3 mc square. For your syllabus content, you don't essentially have to remember or memorize this derivation process, but you have to understand the logics, underlying logics behind it, because sometimes some questions are made, mathematical questions are made depending upon this concept. So if you understand how this whole thing works, it will be easier for you to actually work with those questions. You have some example, I think one example in your worksheet as well. So we're going to see that in time. So you don't have to memorize all this process. You just have to remember this formula, PV equals to 1/3 mc square. To be honest, you can also forget this formula, because this formula would also be given in your formula sheet. But one thing I need to tell you just before I start taking questions, let me elaborate these variables over here. P is the pressure of that gas container. V is the volume of the gas container. 1/3 is a numerical constant. M is the mass of one gas particle, not the entire gas amount, one gas particle. N, capital N, is the number of gas particles over there, which can also be found out by mole number into Avogadro's constant in appropriate cases if the math requires it. And C square is the mean square velocity of the of those particles. Whenever I say mean, I don't have to additionally say average, because mean means average. So mean square velocity is this thing. So this is the whole equation. Now we derived this equation for the case of a cube shaped container, because it was easier for our working. But ultimately, we this equation is equally applicable for all shape of containers. We went for the cube shape because it was easier for us to work with, because so that we could easily replace the area information, and we could easily calculate out the time requirement that was required for our purpose, and we also could use this approximation for our cause. But in any other case, if we have a cuboid shape of container, or a cylindrical shape, or a spherical shape, or any random or parabolic shape, any random shape container, this equation for an ideal gas is equally applicable. So that's the part that we have over here. Further in this investigation, I'm into pore boltechi shobar jonno. I'll take questions one by one. Abiaz.
Sir, in the beginning, is it the distance 2L because the particle comes back to its original position?
No. Between two consecutive collisions, boltechi, the way you can physically visualize the time instance or the time scale for collision on one side of the surface. For example, this was defined as the surface 2. So let's say a particle collides with surface 2. Let's say this is a spike. Then it goes back, hit 1, and eventually come back and makes another collision over here. So then it goes all the way to back to the opposite surface, and then it comes back and it makes another collision. So what I'm trying to show you, that let's say between two collisions, how much time amount is relevant for one collision? So I can pretty well say that the amount of time relevant for one collision is this much, if you go for the idea for time period. Or this much gap is very much similar to this much gap as well, from here to here. So this is the amount of time we require, or if you want, if I draw it more precisely, let's say I'm gonna draw one arrow at the beginning of this collision and finish that time scale at the beginning of the next collision. So here is one collision, here is the relevant time for it. And then there is another collision, then there will be another relevant time for it. So for every single collision with one surface, the particle takes this much time. So this is the time gap between every collision with one surface by one particle. Did it make sense anyhow?
No, sir.
I am trying to represent, let's say, the force exerted. Let's say if this is a graph, let's say the horizontal axis is the time axis. This is the time axis, and on the y-axis, let's say we have the force exerted by the surface 2 on the gas particle. Only force exerted by the surface 2. Every single time you'll have a collision, there will be a force exerted, right? Every single time the gas particle comes in and collides with this surface 2, let's say collides with this surface 2, there will be a force exerted, because this is only the force exerted by the surface 2. After colliding with the surface 2, it's gonna go back, hit surface 1, but that's not our variable, so we didn't give a spike for surface 1 collision. Then it's gonna come back once again and hit the surface 2 once again, assuming that there is not making any collision in between, assuming it's a single particle having unobstructed motion. Like I said, that there's gonna be a lot of generalization. So we are assuming, we're trying to figure out the motion for one single particle going all the way back and forth. That gives us this measurement. So this is one collision with the surface 2, and then it goes to the surface 1 and eventually comes back and makes the next collision. So if you're trying to figure out that how much time is related to one collision,
It's between two peaks.
Yes, bolo.
It's between two peaks.
Between two peaks. That's basically what we did find out.
So between two peaks, each consecutive collision with surface 2, that's how we found 2L.
Exactly. That's exactly why the distance required distance covered was 2L. Because to come back to the surface 2 once again and hit the surface 2 the second time, the particle would have to cover 2L distance, going all the way to the back to the one surface and eventually coming back to surface 2.
Sir, thank you.
Sure, lower your hand. Ashfia.
Sir, my question is kinetic energy conserved in this elastic collision?
Yes. Yes. We are considering the collisions to be perfectly elastic, which was one of the assumptions of the ideal gas that we have seen in the earlier class. That every collision that the particles do with themselves and with the container wall are perfectly elastic, which means no kinetic energy is lost from the particles. It doesn't get added, not get subtracted.
Sir, another question is on this diagram that you are showing on the peaks, between two peaks, why is the distance 2L? I didn't understand.
Because by showing this diagram, I mean, to make this graph would never be required for your volume, for your syllabus volume, but I'm just trying to make sense with you. If we try to plot the force exerted from surface 2 versus time, exclusively surface 2. So we are trying to show over here that at what time instances did surface 2 exert a force onto the gas particle, or other word, at which time instances the gas particle exerted a force on surface 2, only surface 2, not other surface. So the way we describe this is that let's say the gas particle comes in over here with cx velocity, hits the surface 2, and that's when we have one spike. Then it's going to go backwards, hit surface 1, but that is not a part of our graph, so we don't have another peak over here. Then it comes all the way back to the right and hits and makes another hit. So that's another spike over here. So between one spike to the another spike, the amount of distance it has to cover is 2L. So for each collision, so if you consider this graph to be significantly long enough or infinitely long enough, then you can pretty well say that for each collision, the required amount of time is the amount. If I can divide this whole graph into equal spaces, for example, this much equal spaces. So this is the amount of time required for this spike to happen. This much space is the same as peak to peak distance like this, or that can be also said to be equal to be this much distance, that from the start of a collision to the start of next collision. So each collision requires this much time. And within this much time, the total distance that the particle covers is 2L. But we are exclusively considering the collisions with surface 2, not with surface 1.
Sir, when it goes backwards, we don't have to consider that in our graph. Like, we don't include those peaks when it goes backwards again.
No, we are not, because we are only trying to show you that how much force, when was the time instances when the force was exerted on the surface 2 by the gas particle. So force on surface 2 versus time. So it's going to go backwards and it's going to eventually hit surface 1, but that is not going to be included in our graph because we are only trying to plot how much force is experienced by surface 2 exclusively, so that we can find out the total force on surface 2 and eventually divide that by the area of the surface 2, which gives us the pressure. That was the whole aim.
Thank you.
Sure. Mugdho.
স্যার আমার কোশ্চেনটা ছিল যে স্যার মোমেন্টাম ক্যালকুলেশন মানে ফোর্সের ক্যালকুলেশনের জন্য টাইমটা আমরা ওই ইকুয়েশনটা কেন নিচ্ছি, মানে টাইমটা তো পিকের টাইমটা হবে না?
Well, that's the whole idea. I mean, I'll tell you this, that the particles are gonna go back and forth and do collision with the wall. This is okay, but here's the deal. If you think in the larger scale, how do we define pressure? Pressure is defined by the total force exerted by all the particles divided by the total surface area on which the force is working. Isn't that correct?
Yes, sir.
So in a true scenario, the particles are going to be continuously bombarding onto the surface too. It's not going to be a single particle actually in the collision. So if you try to measure the total force on one surface, it's going to be a pretty large amount of collisions happening over the time. Whenever we are considering this happening for a single particle, that's when we only have to consider this F force. So what we are trying to show you, what I'm trying to show you or transfer the information for this figure is that within this amount of time, the total amount of force the particle is going to exert is this much. And then within another amount of equal time, the particle is going to exert that force one more time. But in an actual case, the particles are going to continuously hit the surface. So this, if you consider all the end particles which are colliding with the surface over here, you're going to have a lot of peaks over here, and you can essentially average them out. But other than calculating all of them together, we are calculating one of their behavior, and because we have defined that all the entire ideal gas is made with identical particles, we can extrapolate that behavior further on.
So, sir, we're calculating the most precise point
for one particle. We are trying to calculate the force for one particle, and then we are going to go forward. I mean, I mean, another way I can answer your question. I understand why you didn't get your question answered. Another way I can answer you this question is that we are trying to find out the average force exerted between every collision. I mean,
Okay,
the exact duration of collision is supposed to be negligible compared to the time it takes to in between the collisions that we have learned in our idle gas assumption. So this duration of collision is supposed to be extremely small compared to the duration in between two collisions. That's supposed to happen. So if we calculate this exact duration, this is exactly the time when the particle only is exerting the force. But will the particle be able to exert the force immediately after? No. It has to travel all the way back and come all the way forward. Only then it can exert the next force. So we are trying to distribute the force effect over that time instance and trying to find out the average force for a single particle, because that's essentially what we're going to do for the other particles as well.
Yes, sir, I got it. Thank you.
Sure. Fardin.
Sir, I'm a net user for 5 minutes. I couldn't see the derivation process stuff.
Oh, আচ্ছা, don't worry. আমি এটা লেকচার আপলোড করে দিব, তুমি ওখান থেকে দেখে নিও, নালে আমি ক্লাসে পর তোমাকে আবার বুঝাই দিব. Don't worry about that.
Thank you, sir.
আচ্ছা, মুগ্ধ and Fardin, lower your hand. শুভ্র.
স্যার আমি বলছিলাম যে ab স্কয়ার প্লাস bc স্কয়ারের ইকুয়েশনটা কিভাবে রিলেটেড স্যার, মানে পয়েন্ট টু পয়েন্ট মুভ করতেছে যে
এইটা
হ্যাঁ স্যার, মানে
এটার সাথে এটা রিলেশনশিপ কোথায়?
হ্যাঁ,
here I showed you that the cuboid diagonal would be coming from the square addition of all the three sides. That was the same thing that if we consider that, let's say, well, I'll elaborate your answer. Let's say this is the actual diagonal velocity of the particle c. So আমরা যদি তিনটা axis তিনটা ডিরেকশন আমরা এদিকে হচ্ছে x axis, এদিকে হচ্ছে y axis, এদিকে হচ্ছে z axis. So I could very well write that if this is my cx component, this would AD would be my cy component and AE would be my CZ component, right?
Yes, sir.
So I just replace that AD component over at BC and I replace the AE component over at CG so that I could get this right angle pathway to reach to the same point, which brings us to the same equation like this one.
Okay, so that is we are getting the resultant force, resultant speed, sir. Somewhat like that, right?
I'd say velocity.
Yeah.
C represents the resultant velocity, which is coming as the vector sum of Cx plus Cy plus Cz. That's for the vector equation. But if you want to go for the magnitude calculation, you essentially have to give the squares because of the Pythagoras law.
Yeah.
বুঝা গেছে?
Yes, sir.
Okay, Abiyaz, you seem to have one more question.
Yes, sir, it's just a short one, but during collision of the particle and the wall, isn't it almost instantaneous because there's almost no squashing of this particle?
Yes, it's almost instantaneous, or the collision duration is negligible compared to the time instance between the collisions. The answer to your question is yes.
So we can think of it because the particle does not squash is the reason, and this collision time is negligible compared to the traveling time.
Yes. If you want to physically visualize this, I mean, if you want to physically visualize, did I show you the squashing effect of the golf ball ever?
No.
No, sir. Sir, level someone at that.
Take a look. This is a golf ball hitting a steel surface, and that's what happens in a high-speed camera. Check this out. This actually expands that much. This is a solid object, by the way.
Damn.
Yep. This is another view, which does not essentially cover, I think,
the world. Thus, about.
No, this is just okay. This is the wow. I paused at the perfect nick of the time. Wow, my hands are magic. So
yeah.
So here it comes, and the golf ball is being hit at this point. So you can see how much squash is it done. So Abias, the reason I showed you this, that this is actually what happens for physical collisions. I mean, it happens over a very short amount of time. These are extremely high-speed cameras. The frame rates are insane. That's why we could actually see this slow motion figure. But for your visualization for ideal gas, you should consider that nothing like this happens. The particle comes in, plops with the surface, and bounce back immediately. There is no shape change. There is no duration.
It's kind of crazy to actually see it happen.
And sort of like exactly what we see in our eyes. We see that collision. For our brain's slow reaction time, we perceive the collision to be instantaneous. So you can consider that as well. But you have to assume that there is no deformation. But actually there is some deformation. But for ideal gas, we generalize it to have not any deformation and not any time duration at the same time.
Yes, sir. Thank you.
Sure. Shubro.
Sorry, sir. Hand lower kora hoyeche.
Oh, acha, no problem. So এটা গেল। এরপর আমাদের কিছু ফার্দার কিছু ডিসকাশন আছে। ফার্দার ডিসকাশন মানে হচ্ছে সরি, আচ্ছা এই পেজটা একটু উপরে হয়, তোমরা একটু কষ্ট করে এই পেজটা করো। আমি I'll try to correct it in the next versions. এরপর হচ্ছে আমাদের কিছু অ্যাডিশনাল ক্যালকুলেশন আছে। অ্যাডিশনাল ক্যালকুলেশনগুলো আমরা একটু দেখি যে ফার্দার ইনভেস্টিগেশন। এটা হচ্ছে যে PV equals to nRT. This is the ideal gas equation that we have come across in our last class. Today we just learned that PV can be also 1/3 mc square. It is very important that you do know the meaning of each of these variables which are in this equation. Pressure, volume, inside volume of the container. This volume essentially means the volume of the gas, which essentially means the inside volume of the container. It doesn't necessarily mean the container volume of the gas. I mean, you have to understand what does it mean by the volume of the gas. Volume of the gas means the inside volume of the container. This n means mole number, small m. R is the molar gas constant, 8.316 or 314, 8.314. T is the thermodynamic temperature of the gas, or Kelvin temperature. You can write that as well. Here PV is same. 1/3 is numerical constant. M is the mass of one gas particle. Capital N is the total number of gas particles, which can be calculated by mole number into Avogadro's constant. And C square is the mean square velocity of those particles. Average K and kinetic energy of one molecule can be given by half mc square. Because this square is the mean square speed, and this square equals to C1 square plus C2 square plus Cn square divided by n. And so this is this thing. So I don't understand what is written over here. আচ্ছা হ্যাঁ, পোলাপান অনেক সময় যেটা মিসআন্ডারস্ট্যান্ড করে যে this is mean square velocity, not whole square. So it should not be written as C1 plus C2 whole square by n. You square then mean, not mean then squared. বুঝছো কি বলছি? এই এক্সপ্রেশনটা মানে বুঝো, or try to compare these two expression. This is supposed to be C1 square plus C2 square plus Cn square divided by n. Not supposed to be C1 plus C2 plus C3 plus Cn whole square divided by n. Not that one. So do not confuse this.
Sir, আমরা স্কয়ার করি স্পিডের জন্য, রাইট?
হ্যাঁ, ম্যাগনিটিউডটাকে বের করে আনার জন্য, ডিরেকশনটাকে অবলিটারেট করার জন্য।
নাও স্যার লাস্টে যে আমরা যখন বলেছেন যে c স্কয়ার ইকুয়াল টু cx স্কয়ার প্লাস cy স্কয়ার, ওখানে তো বেসিক্যালি আমরা রেজাল্টেন্ট স্পিডটাই পাচ্ছিলাম ইন স্কয়ার্ড ফর্ম, রাইট?
Yes. So now we are gonna over here we are going to equate these two equations. nRT equals to 1/3 mc square. So n is the mole number. Mole number was converted into n by Na. RT remains same. Nn cuts off each other, and then we have R by Na. R by Na is another constant that's called the Boltzmann constant. So there is an easier way to understand what that is. It's not what it's called, what I'm about to describe. Molar gas constant is the gas constant for 1 mole of particles. 1 mole of particles means how many particles? Avogadro's constant equal number of particles. If you divide that molar constant by the Avogadro's constant, you get the Boltzmann constant, which is the same thing. It is the same gas constant, but it's applicable for one gas particle. So R by N, Avogadro's number, Avogadro's constant, gives you the Boltzmann constant, which is replaced over here. So this get actually circled over here, which is a very good thing. Actually, he showed that which was replaced. So we did this thing, replace over here. Then we brought the R on top and keep everything same. N was cut off, so N is not written over here anymore. R by Na equals to R by Na T equals to 1/3 mc square. So Kt equals to this thing. Now we want to make this expression into half mc square so that we can replace this. We can put the average K of molecules over here. So what we did, we wrote half mc square and we wrote the compensating 2/3 over here. A theta হচ্ছে আগে 3 and this half is compensated by this 2 extra 2 over here. So inside the bracket, inside this square bracket over here, we have a half mc square, which is the average kinetic energy of one gas molecule. So you can write Ke average, Kt equals to Ke average, or Ke average equals to 3/2 Kt. This 3/2 K is a constant and T is only the thermodynamic temperature. Now from this equation you can see that K average equals to 3/2 Kt. If you take out this constant out of this equation, you can convert this into a proportionality, which gives us average kinetic energy of an ideal gas particle is only, this only word is very important, average kinetic energy of an ideal gas particle is only dependent on its thermodynamic temperature. Because like I said in the discussion in the last class, that for the case of ideal gas assumptions, that for ideal gas particles do not exert any force onto each other except for when they are in collision among themselves and also with the container wall. Apart from that, they don't have any force between them. That's how we have generalized the idea of ideal gas. So that's why the total kinetic energy of the gas molecule, of an ideal gas molecule, is exclusively dependent on its temperature. So this is a very important proportionality equation. We have to answer quite a good number of theoretical questions using this concept, which is gonna follow further in the worksheet process. Furthermore, if we see, we can also you convert this equation a bit more. PV equals to 1/3 mc square. Mn, if you have a look at these two variables, m is the mass of one gas particle and n is the total number of particles. If you multiply these two factors, you can essentially get the total mass of the gas. Mass of one particle into the total number of particles gives you the total mass of the gas. So this Mn was written as total mass of the gas. This is not a division line, this is just an underline. So this is total mass of the gas, and we brought the V over here. So we can write total mass of the gas divided by volume, which ultimately gives total mass by volume makes into density. So pressure equals to 1/3 rho c square. That's also another useful equation which we can use for our purpose. So all the box equations that you can see over here would be required for our worksheet solution for mathematical purpose or for theoretical questions. And all the derivations are over here. You don't essentially have to remember them, but you can get across to understand them. Just before I move on and start taking your questions, I'd like to show you one more thing, and then I'll take your questions. The thing that I'm trying to show you is you have come across quite a good number of questions over here. So it might as well be worthy of our effort to have a look at how many of these constants would be made available to us in the formula sheet. Have a look. These are numerical constants you will have available. You have permeability of free space, permittivity of free space, elementary charge, Planck constant লাগবে পরে ইনফেরাইমেন্ট মাস, এটা লাগে আমাদের মোমেন্টামের সামের জন্য লাগে, এবং হচ্ছে আমরা যখন when we will go for the thing এই যে here it is. Molar gas constant is 8.31 joule per Kelvin per mole. Avogadro constant is 6.02 into 10 to the power 23 per mole. The Boltzmann constant is the division of these two, that is 1.38 into 10 to the minus 23 joule per Kelvin. And these are the three things of the gas law that you're going to have as constant value available to you. As for the formula part, work done on a gas is a formula is given. Work done is given by pressure, constant pressure into change in volume. You're going to have this formula available. Hydrostatic pressure is P equals to rho gh. That is going to be available. Pressure of an ideal gas, this is going to be available. So pressure of an ideal gas is given by 1/3 Nm by V c square. So this whole thing is basically density, but they divided this into expressions so that you understand this part. Then do we have anything else? We don't have anything else about the entire thermal chapter over here, which means all of the other formulas, for example, the governing formula for thermometers, which is change in thermometric property is proportional to change in temperature or change in thermometric property. That one, then Q equals to MC delta theta, Q equals to MLF, Q equals to MLV. All of these equations have to come from inside your brain. So you gotta be careful about to remember those things and not to mess up. Okay, I'll take questions. Sajid.
Sir, ওই n এটা কোথা থেকে আসছে স্যার?
এটা That's how we define mole number. How do you define mole number? No. I'll help you to get this number. Let me tell you this thing. Avogadro's constant is used to count how many of the same thing is available within a certain
number of molecules.
n টা হচ্ছে number of molecules, n হচ্ছে Avogadro's constant. So হ্যাঁ, mole number টা ওখান থেকে আসছে।
আর স্যার আরেকটা হচ্ছে 2/3 টা করতে 2 টা করতে স্যার।
এখানে আমরা half দিছি, we gave a half over here to make it into k, so compensating 2 is on the numerator side. Okay. Yes, Abiaz.
Sir, when there is only one particle, is PV equal to kinetic energy, or does it not apply at that point?
আবার বলো, বুঝি নাই।
When there is only one particle, does PE equal to KE? PV equal to KE?
Well, honestly speaking, this entire, once again, recall the first statement of the ideal gas assumption. There has to be enough number of particles available so the statistical approach can be applied. These set of equations are applicable for a good number of particles present in your container, so that you can apply the concept of statistics. For example, the concept of statistics being that Cx equals to Cy plus Cz. That is the most gross or most powerful statistical approximation that we used to derive this formula of PV equals to 1/3 mc squared. So the answer to your question is, if you have only 1, 2, or even 10 particles, you cannot apply these equations for those things. In those cases, you have to individually locate those particles and be able to measure their kinetic energies at time instances. You can only apply this set of equations when there is a big enough particle number, so the statistical approximation can be applied. So the question to answer is that if you are considering that in a container we have somehow made sure to enter or to allow only one gas molecule inside this thing, can we use this equation for those particles? The answer is no.
Okay, sir. Thank you.
Did I make sense?
Yes, sir, because it's not a large enough number to pull statistical approximation.
Beautiful. Fardin.
Sir, আমার chemistry ছিল না, so I'm not getting why মানে n by n এ কোথা থেকে আসছে।
হ্যাঁ বুঝছো?
না একটু like
আচ্ছা বুঝতেছি। I'll give you a very simple example. Avogadro's constant is very much like a full number of objects which we're going to call a certain group. Consider the idea of dozen. How many is 1 dozen?
Sir, 12.
12. So if you're buying, let's say 2 million bananas, you can also call it that I am buying this many dozens of bananas, right?
Yeah.
Avogadro's constant is very much like that. If you have 6.02 into 10 to the power 23 number of identical things of a certain object, those things together is going to be said, is going to be referred to as 1 mole.
All right.
So if you have n number of particles and you divide this by the number of Avogadro's constant, you get how many moles are there. So mole number is basically equals to total number of particles involved divided by the Avogadro's constant. So you get a number that how many moles are there. For example, how many dozens are there? Similarly, how many moles are there?
আচ্ছা ঠিক আছে বুঝছি বাট আচ্ছা 2/3 টা কোথা থেকে আসছে?
আচ্ছা 2/3 বলতেছি এই পার্টটা বুঝছো?
Yeah, sir, বুঝছি।
The 2/3 is coming from the idea that 1/3 was the default part from the equation of 1/3 mc square. We wanted to bring about this expression half mc square within this equation. So inside the bracket we wrote half mc square. So we replace m comes in, c square comes in, but we wrote the half because we want to get the average k involved in this equation. So the 1/3 here 3 চলে গেছে এখানে, and because we gave an extra half over here to compensate that we gave a 2 over here.
মানে বেসিক্যালি আপনার লাইক 2টা কাটার জন্য আমরা লাইক 2 উপরে দিয়েছি,
হাফটা কাটার জন্য উপরে 2 দিতেছি,
হাফটা কাটার জন্য উপরে দিয়েছি। বুঝছি স্যার, থ্যাংক ইউ।
All right, that's pretty much it from the thermal question paper. I'm gonna help you solve some problem right now. So তোমাদেরকে তো থার্মালের ওয়ার্কশিট দিনাই দিছি?
No sir.
আচ্ছা থার্মালের ওয়ার্কশিট আমি রাতে দিয়ে দিব। একটু আমার কাজ করা বাকি আছে থার্মালের ওয়ার্কশিটে, সো থার্মালের ওয়ার্কশিট আমি তোমাদের ক্লাস শেষ হওয়ার কিছুক্ষণ পরে আপলোড করে দিয়েছি। But I might as well start solving some question with you so that we can take part in the process.
Sir, is thermal the smallest chapter in the entire A2?
In terms of worksheet volume, I'd highly say no. But maybe in terms of concept, it is yes. I'll tell you why in terms of concept is yes. Because a lot of the conceptual discussion I did not cover in this chapter, in the theoretical part. There are a lot of maths which you're gonna see, which is gonna involve the idea of thermal equilibrium, which is gonna be long enough to have ideas which I cannot find a way to cover in the theoretical discussion because they are relevant to a specific problem type. So we still have quite a bit of theory to discuss, which would be popping up at times when we reach to that exact problem in our worksheet. But I cannot specifically make a yes or no question answer to your question because I honestly don't know that.
Oh.
Okay, where was I? পোলাপান আমি যে এই যে লাস্ট 2-3 ক্লাস ধরে ক্লাসের শুরুতে তোমাদেরকে গান বাজনা করাইতেছি, তোমরা প্যারেন্টসদের কাছে ঝাড়ি খেয়েছো কে কে?
স্যার প্যারেন্টস জিজ্ঞেস করছে কি হয়েছে।
আমাকেও জিজ্ঞেস করছিল।
আচ্ছা, কি জিজ্ঞেস করছিল? যে কি হইতেছে ক্লাসে?
হ্যাঁ
এটাই জিজ্ঞেস করছে স্যার।
And then what was your response?
I basically said যে it's like this entertainment thing, you know, her dance class so that বাচ্চাদের আমাদের মুড ভালো থাকে during class. So yeah.
And what is the repercussion of that statement that you made? What was the aftermath of your statement?
Oh, and then she said, oh, acha, it's okay. And then she went away.
Acha, okay. So, I mean, I have a logical reason, although I don't have to explain this to you because I'm the omnipotent in this place, not so. But I still want to give an explanation. I mean, if you ever become teachers, I mean, it's always a good thing to make your audience be able to more keen to listen to you before you start actually delivering the product, which in this case is the lecture. Because let's say you are in somewhere else, you just started the class and you are seeing that thermal lectures is happening at full phase. You might as well require 5-10 minutes to just to be able to bring all of your concentration in different places and put it into your device, into your screen. So it's not a bad idea to have some sort of music so that you are all at least calmed and you are enjoying the process. And then we slowly divert your brain. Okay, now comes the thermal. So you're sliding in the thermal lecture after the music. So our brain can be a bit fooled in that process. So that's how the subconscious works. So that's the whole point. I'm learning this stuff by watching a lot of random YouTube videos and sort of believe them, some of them. And in essence, you could start being a bit of a guinea pig over here. So don't mind that.
Sir, no one in the class minds that, honestly speaking.
Yeah.
Well, you cannot speak for everyone.
So what you're doing is great.
There can be someone who might actually have some confusion about this. That's why I wanted to clear that up. But they might not ever speak up, which is also a part of the audience judgment that you have to have if you ever gonna be a spokesperson ever in your life.
So আপনি ফার্স্ট মানুষ না যে ক্লাসের আগে গান গাইতেছে, গান গাওয়া ভিডিও share করছে.
So I'm not the first one.
No, you are not the first one.
Oh, awesome. Sajid, you are a lucky guy.
Thank you, sir.
You understand the context, right?
Yes, sir.
Good. So if we have a look at from the very first question, why not? So have a look over here. The kinetic theory of gas leads to the equation half mc square equals to 3/2 kT. Explain the significance of the quantity half mc square. আচ্ছা, এটা একটা কোশ্চেন। আমি কোশ্চেনটা পুরোটা বলতেছি, পরে সলিউশন বলতেছি। Is the equation to suggest what is meant by the absolute zero temperature? Okay, the first thing that is important that explain the significance of the quantity half mc square. এখানে স্টুডেন্টরা খুব কমনলি যে কাজটা করে সেটা হচ্ছে they forget to write the word average. First, the way I would write the explanation of this question, there's a 3 mark over here and there's equal 2 line space, 2 line space. So there is no way you could possibly guess that which of this question has 2 mark. I mean, obviously 3 mark is not going to be divided into 1.5, 1.5 because there's no fractional marking in your syllabus, in your exam mechanism. So one of them has to have 1, other one has to have 2. So you don't know which one is which. So I'm going to provide 2 mark worthy of answer for both of them, just to be on the safe side. That's just how I prefer to do my stuff. Because I cannot say, if they gave 1 and 2 over here, I would be happy. I'd be happier, but in this case, my hands are tied. So I'm gonna write this answer in this fashion. Half mc square is the average kinetic energy of the gas molecules, plural. Full stop. Then you can write m is the mass of one gas molecule, c square is the mean square velocity of the gas molecules. You have to understand, mean square velocity is not the property of a one particle. It is an average property of all the particles, right? So I think to singular and plural shouldn't be a bit of a trouble. Okay, you can write either way. So I'm gonna first say what this whole thing is, and then I'm gonna specify what these symbols individually refer to. I'm gonna go for that as well. Use the equation to suggest what is meant by absolute zero temperature. Have a look over here. 3/2k cannot be 0. Can it be 0? Respond.
No, sir.
3/2 is a numerical constant. K is a Boltzmann constant. This cannot be 0. Here, this is the mass of the gas particle. Ideally speaking, this cannot be 0 as well. Which means, if the temperature has to become 0, absolute zero temperature that is, absolute zero temperature has to be 0, the only thing that can become 0 is c square. So this brings us the idea of the absolute zero temperature is that the temperature at which the mean square velocity of the gas molecules becomes 0 / the particles stop moving is the temperature of absolute zero. So if you have to make this 0, have a look at the equations, very, very, very mathematical. If you have to make this 0, you have to have this thing 0 because everything else cannot be 0. So the absolute zero is the temperature where the mean square velocity of the gas particles becomes 0 / particles come to rest, or gas particles come to rest. Or you can write ideal gas particles comes to rest. I mean, the further detail you can put in, better. Examiners will know that you know your stuff. That makes a very good impression and helps you get better marks throughout your paper.
Sure.
Yes.
Absolute zero te rest আসতেছে যে ওরা না প্রত্যেক সময় constant random motion আছে তো ওরা zero তে কিভাবে আসতেছে?
That's the whole point. How we define the idea of absolute temperature, thermodynamic temperature. It is actually, I mean, sorry, let me answer your question. They are in random motion anywhere above the absolute zero temperature. Because you can see that so if you reach to absolute zero temperature, if you can somehow reach that, which is physically impossible to achieve in our earthly environment, scientists tried that, but couldn't happen. They went very close, but they couldn't reach to the very lowest point. But they might as well be, because researchers are pretty fast. I mean, there was a point, there was a mechanism that, I mean, if you come to think about it, how can we extract heat out of an object? By putting it into contact with a much cooler object, so that the hot object would lose heat to the cooler object. So if you want to make something absolute zero, you have to extract heat from that object using an object that is cooler than that. Do you get my point? Now, that is fundamentally inconsistent within the statement.
It's impossible.
Yeah, that's what I said. It's fundamentally inconsistent within the statement itself. So that's difficult to do. So what the scientists are doing, I mean, the recent YouTube video that I came across, that some scientists in the world, they are now using high frequency laser to make cooling effect on a piece of metal. Somehow they're achieving this. I didn't get the whole idea, but that's the concept that the methodology that I could extract out of the whole video, that some sort of specific frequency and intensity laser shining upon a certain specific type of material was producing some sort of cooling effect, which can bring us to a temperature much closer to 0 Kelvin. But exact 0 Kelvin is still not achieved yet, that I know for a fact. As far as my idea goes, it's not achievable, but well, you never know. We're going to have a look at the mark scheme just to be sure. Have a look. Have a read at the mark scheme for number A, and also the examiner's report, and tell me any question you have. Use your eyes.
স্যার কে টা কি জন্য স্ট্যান্ড করে একটু বলতে পারবেন?
Boltzmann constant.
Sir,
Yes.
triple point of water or its freezing point, মানে কি?
The point of pressure and temperature where water is 3 states at once.
Yes, that's the triple point definition. And freezing point essentially is an exclusively temperature relevant point. Freezing point or boiling point are refers to only temperature. They do not inherently incorporate a pressure information. I mean, but what is important that if you want to specify a certain freezing temperature of an object or a boiling temperature of an object, you have to mention a specific pressure for which it is applicable. For example, at one atmospheric pressure, the boiling temperature of water is 100 degrees Celsius. At one atmospheric pressure, the freezing temperature of water is 0 degrees Celsius. So boiling point and freezing point essentially mean a temperature value where a certain pressure has to be included, but it is not inherently included. It has to be externally mentioned. Whereas for the triple point of water, it means a combination of pressure and temperature at which all the 3 states of the water can coexist together.
Acha, acha.
You can look up some YouTube videos where people are trying to recreate this situation where water can continuously switch between 3 stages. There is one of these videos which I actually came across where some people actually created this scenario using a liquid nitrogen and air pump for the triple point of carbon dioxide, which is easier to work other than water, I think. I'm not sure why. So they had a situation where you could have solid, liquid, and gaseous state of carbon dioxide. So which is a pretty cool experiment. I'm not gonna go ahead and find this one, but I'm telling you, if you're curious, you will be able to find that, where there was in a enclosed container by using a very special pump, and also by using liquid nitrogen, they reduced the temperature and the pressure to control to such an amount that it was a triple point of carbon dioxide, where you had some liquid carbon dioxide on the petri dish, and above the liquid carbon dioxide there was a piece of solid carbon dioxide, which was continuously running back and forth because it was continuously converting into gas on its bottom side somehow, and it was once again sublimated from the top surface. So it was ever building up on the top and losing it from the bottom. So it was a pretty nice thing going on.
Okay, sir.
Are they on any equilibrium or something?
Yeah, it essentially means they're in equilibrium. They're in equilibrium means that the exact amount of energy that you did give, the exact amount of potential energy and the kinetic energy that you made those molecules to have at that stage, that amount of potential energy and kinetic energy combination allows them to exist at any of the states. বুঝতে
সো তার মানে কনস্ট্যান্টলি ধরেন কাইনেটিক এনার্জি থেকে পটেনশিয়াল এনার্জি চেঞ্জ হতে থাকে বা এরকম কিছু যাতে স্টেটটা চেঞ্জ হতে পারে
that can happen continuously for a group of particles. Once again, if you have a big number of particles, the total average change can be considered to be 0. But for any specific molecule, it can belong to the gaseous regime. It can immediately come to the liquid regime, or it can go to the solid regime, or it can go back and forth from any of the 3 stages directly. I mean, you can have sublimation, reverse sublimation, boiling, freezing, melting, vaporization. Everything is happening simultaneously. I mean, the 3 phases are simply going across each other. All the molecules had the individual capability to exist at any of those stages.
স্যার একটা কোশ্চেন ছিল।
বলো
স্যার বলছিলাম যে আমরা কি পুরোটা আইডিয়াল কেস কনসিডার করছি?
For all of your mathematical questions and all of your theoretical questions as well, unless the question specifies that considering it as a real gas, you will always consider them to be ideal gas, always. Because this equation that we had started our equation by half mc square equals to 3 by 2 kt was entirely built up upon the idea of an ideal gas.
Sir,
bolo
স্যার যদি রিয়েল গ্যাস হতো তাহলে তো প্রেসার থেকে একটা কম্পোনেন্ট মাইনাস করতে হতো, ভলিউম থেকে আরেকটা কম্পোনেন্ট মাইনাস করতে হতো।
না, প্রেসারের সাথে একটা কম্পোনেন্ট অ্যাড করতে হতো আর ভলিউমের সাথে একটা কম্পোনেন্ট মাইনাস করতে হতো, বাট দ্যাটস নট, হ্যাঁ 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 সেটা করতে হতো, বাট সেটা আমাদের ফিজিক্সের এ টু সিলেবাসে নাই সামহাউ। You don't have to bother for that. Okay, have a look at question number B. Two insulated gas cylinders A and B are connected by a tube of negligible volume as shown in figure 3.1. So we have tap and we have cylinder A, cylinder B. This cylinder has an internal volume of 2.0 into 10 to the minus 2 meter cube. Initially the tap is closed and cylinder A contains 1.2 mole of an ideal gas at temperature of 37 degrees Celsius. So we are given information about cylinder A. Cylinder B contains the same ideal gas at pressure 1.2 into 10 to the 5 Pascal at temperature of 37 degrees Celsius. So both of them has the same temperature, 37, but the difference is that this one contains a mole number of gas of 1.2 mole, whereas this one contains the pressure at 1.2 into 10 to the 5 Pascal, and the tap is currently closed. So okay, calculate the amount in mole of the gas in cylinder B. So we can calculate this up pretty simply. PV equals to nRT. You have the P available, you have the V available. You're trying to calculate N. R is a constant. T can be obtained from this one. So if you use PV equals to nRT, we can pretty well calculate this equation, which they calculate over here. N equals to PV divided by RT. So you get 0.93 mole, which works out. Then the question says further, the tap is opened and some gas flows from cylinder A to cylinder B. Using the fact that the total amount of gas is constant, determine the final pressure of the gas in the cylinders. Using the fact that the total amount of gas is constant, determine the final pressure of the gas in the cylinders. Now, try to understand. Whenever we will turn on this tap, some gas travels from cylinder A to cylinder B. So this essentially tells us that cylinder A pressure was higher compared to cylinder B, because as per the question, they have the same temperature. If gas has to travel from A to B, A was maintained at a higher pressure compared to B. Now we are asked to calculate the final pressure of the gas in the cylinders. How do you think we can do that?
Yeah, specific heat capacity?
No, we don't have any amount of energy heat transfer over here.
So we can use that like PV equal to nRT, and you make an equation out of it, like P1.
So PV equals to nRT, you are going to apply for which cylinder? Cylinder A or cylinder B?
Both of them, sir. Like
for
starting like initially A, then both of them, because the tap is open and now the gas occupies both of them.
That doesn't make sense. I mean, initially using A, you can calculate the initial pressure of container A if you apply for the information for container A. But how does that help you to find out the final volume of the gas? Sorry, final pressure of the gas, because you can very well calculate the initial pressure of cylinder A. You're not held up there. PV equals to nRT gives you the pressure of cylinder A. So you're going to have a higher pressure compared to here. So this is on his 1.2 to 10 to the 5 Pascal. You're going to get a higher value over here. That goes without saying. But how can you eventually combine those two factors to get the total pressure of the two containers? Are you simply going to average them?
Sir.
Bolo.
Sir, ইয়ে করা যায় না, মানে আমরা ভলিউম অ্যাড করে দিতে পারি না সেকেন্ড ফাইনাল ইকুয়েশনের জন্য?
Yes, we can. And there's one more thing that you have to specify, which I'm waiting for.
Sir, সি তে কোনো চেঞ্জ আসবে?
সি তে মানে? সি তে মানে?
স্যার লাগবে তো ফাইনাল প্রেসার।
Yes.
তো আগের প্রেসার জানা আছে আর আগের ভলিউমও তো জানা আছে।
আগে হ্যাঁ হ্যাঁ।
তো ফাইনাল ভলিউমের জন্য ফাইনাল ভলিউম ইনটু 2 করতে হবে, আর P1 V1 = P2 V2 দিয়ে করা যাবে না?
তুমি এটাই আমি বলতেছি যে তুমি যদি P1 V1 = P2 V2 করো, that is applicable for a fixed amount of gas. Boyle's law is applicable for a fixed amount of gas maintained at a fixed temperature. এখানে তো কোন সিলিন্ডারে ট্যাপ খুলে দেওয়ার পর তো কোন সিলিন্ডারে আমার মোল নাম্বার অফ গ্যাস সেম থাকতেছে না।
So we can just add the moles for cylinder A and B.
Exactly. This is the additional information that I was waiting for to pop up. So what I mean is, let's say if I take this picture out, Okay, so what I'm trying to mean is that we can essentially try to solve this problem for that final pressure. We can go ahead and write this, that P into 2V, I might as well write 2V. Why am I at 2V?
Total volume.
Total volume is now 2.
2.
Of the origin.
দেখো এই কোশ্চেনে দেখো বোঝা যাচ্ছে কিনা। After the tap is open, the gases will eventually transfer over in the two containers. The total volume that the entire amount of gas is gonna cover is the total combined volume of the two cylinders. So now we are considering this equation for the entire gas that we have available in both of the containers together. So we're considering the whole gas as a single system, which are connected by this tube. So P into V equals to nRT. Now the total amount of mole number should be the initial mole number plus final mole number. Now if you want to think about the mole numbers should be available to us. The question already gives us the mole number for the first cylinder, you see over here, and you just calculate the mole number in the second cylinder over here as well for this one working. So you know the total mole number for both of them, which means you know Na, you know Nb, you know the value of V. R is a constant, T is the thermodynamic temperature, which is 273 plus that much. Boltzmann, একটা জিনিস খেয়াল করো, I would highly recommend that in your working you should use 273.16 for your calculation. This would be preferable. I mean, preferable কেন বলতেছি, there are certain maths where if you do not use 273.16, you're going to have small bit of errors. But if you do use 273.16 other than using 273 exclusively, you're going to get correct answers almost in all cases. Because one of the problem that is that thermodynamic temperature of or the Kelvin temperature is defined. I mean, for the sake of simplified version, we say that 0 degrees Celsius equals to 273 Kelvin, but the actual value is 273.16. এই 0.16 এর একটা ইমপ্লিকেশন আমাদের ওয়ার্কশিটে কোনো না একটা কোনো কোশ্চেনে আছে, অথবা তোমরা যদি এই ওয়ার্কশিট সেশনগুলোর পরের কোশ্চেনগুলি করো তাহলে পাবা। My worksheets are compiled up to W13. এই কোশ্চেন বুঝা গেছে everyone? So this is number 2. Let's have a look at the mark scheme. Total amount of gas is this many moles. So they are explaining this much this for you to show this, and they have done N equals to total volume into pressure divided by RT. So they have used N equals to PV by RT. I don't know why they use this equation. Well, honestly speaking, this is a very old mark scheme. You can have a look at the writing of the mark scheme writing. So it's a very old question. Anyway, they have basically used PV equals to nRT over here and find out the final pressure. It was pleasing to note that very few candidates failed to use Kelvin temperature in the equation. Double negative. Okay. As a result, this part of the equation was answered well. In two significant minority did not appear to know how to attempt the question. However, there were many correct solutions with adequate explanation. Makes sense. আচ্ছা, এটা একটা প্রবলেম গেল। আমি আরেকটা প্রবলেম দেখাবো যে
স্যার বেসিক্যালি আমরা সব সময় কি অ্যাবসলিউট টেম্পারেচার নিয়ে কাজ করব?
Well, capital T stands for absolute temperature. Theta stands for degree Celsius.
Yeah.
আচ্ছা, এখানে মনে হয় আমি ওরকম একটা কোশ্চেন পাবো না। আমি তোমাদেরকে নরমাল একটা কোশ্চেন প্র্যাকটিস করাই। পোলাপান, তোমরা একটা কোশ্চেন লেখো, কাগজ কলম নাও।
কোশ্চেন লিখবো স্যার?
হ্যাঁ, একটা কোশ্চেন লিখো, আমি ডিটেক্ট করতেছি। কোশ্চেনটা মনে হয় আমার কাছে থাকার কথা। আমি একটু দাঁড়াও দেখি জেসিকার শেয়ার করা পেজেস গুলোতে আছে কিনা, থাকতে পারে। জেসিকা তো আমাকে একটু পেপার শেয়ার করছিল। আমার খালি ঘুম পায়। আমার কেন খালি ঘুম পায়? তোমাদের একটা ফিলিং এর ব্ল্যাঙ্ক দিছিলাম, ফিলিং এর ব্ল্যাঙ্কটা কে কে দেখছিলা?
আমি তো ফিল আপও করছিলাম।
Yes. Someone guess what was my most preferable answer?
আমার একটা মোটা বিড়াল আছে।
That's true, but বিড়াল শুকায় গেছে এখন আর বিড়াল মোটা নাই।
আরে কেন কি হইছে?
এক নাম্বার হচ্ছে বাচ্চা হইছে, so that was a mass subtraction, and then বাচ্চাদেরকে খাওয়াইতে শুকায় গেছে।
আরে
স্যার ওই বিড়ালটা দেখলাম একটা কথা একটা ওয়ার্ডই মনে পড়ে।
কি? মোটা?
না স্যার, ইউ গেট ইট।
ও আচ্ছা,
আমি আপনাকে বলছিলাম।
সাজিদ ভাই।
Okay. Open secrets be open secrets, ঠিক আছে, but still they keep them in the secret region. আমি কি খুঁজতে আসছিলাম এখানে? জেসিকা। I mean, when I actually gave you that fill in the blanks, the thing that was popping in my head, I was really sitting on my chair and I was lazy. কাজ করতে ইচ্ছা করতেছিল না, so I was looking around and then my eye got stuck on my own stomach. So I felt like that আমার অনেক বড় একটা ভুঁড়ি আছে, so like বিশাল ভুঁড়ি. Weird flex, but that was the point.
At this point, a lot of people do, sir. It's fine.
Something to be proud of.
True that.
This is the math that I'm talking about, but I do not have the question over here. I think I made the kids write this question, and then the students did not feel like, or maybe they didn't copy it, or maybe I asked them not to copy it. I don't remember. Actually, it's question লেখো, কাগজ কলম নাও, question লেখো, আমি question বলতেছি। Or should I write down the question? না, তোমরা লেখো, চুপ থাকো।
Dictate.
হ্যাঁ। লিখো specific heat capacity of water, comma CW মানে হচ্ছে এরকম small c subscript w. Specific capacity of water, comma CW equals to 4.2 into 10 to the power 3. 4.2 into 10 to the power 3 joule per kg per Kelvin. নিচেটাতে লিখো, নিচে লিখো specific capacity of ice, comma CI equals to 2.1 into 10 to the power 3 joule per kg per Kelvin. 2.1 into 10 to the power 3 joule per kg per Kelvin.
Sorry. Value?
2.1 into 10 to the power 3.
Sorry, water টা কত ছিল জানি?
4.2 into 10 to the power 3.
এইটা তো আইস, যেটা বললাম লাস্ট।
হ্যাঁ, পরটা আইস। আচ্ছা, এরপর লিখো, নিচে লাইন লিখো specific capacity of steam, comma CI equals to 1.2 into 10 to the power 3.
CI sir or CS?
CS steamer জন্য CS লিখো, CS equals to 1.2 into 10 to the power 3 joule per kg per Kelvin.
Yes, sir.
এর নিচে লিখো specific latent heat of melting of ice, specific latent heat of melting of ice, specific latent heat of melting of ice equals to 3.4 into 10 to the power, দাঁড়াও, ভ্যালুটা হচ্ছে আসলে এরকম 336000, এটাকে 3.4 into 10 to the power কত হয়? 5 হবে না?
Yes, sir.
হ্যাঁ, 3.4 into 10 to the power 5 joule per kg. এটা লেখা হচ্ছে LF LF সিম্বল হচ্ছে LF L স্মল l সাবস্ক্রিপ্ট F এর নিচে লাইনে লিখো specific latent heat of vaporization of water specific latent heat of vaporization of water comma LV equals to 2.7 into 10 to the power 6 joule per kg না 2.7 না এটা হচ্ছে 2.6 2.3 sorry 2.3 into 10 to the power 6 joule per kg আচ্ছা এই পর্যন্ত হচ্ছে সব কনস্ট্যান্ট এখনো কোশ্চেন শুরু হয় না এখন কোশ্চেন বলতেছি কোশ্চেন নাম্বার 1 লেখো question number 1 Ashfiya, you raised your hand. Did you have any question about anything? Oh, you just dropped your hand. Okay. Question number 1 likho. 2 kg water at 10 degrees Celsius is mixed with 4.3 kg of water at 62 degrees Celsius.
স্যার আবার বলবেন
আমার তো ভ্যালু মুখস্থ হয় নাই
2 kilograms of water at 10 degrees Celsius is mixed with 4.3 kilograms of water at 62 degrees Celsius.
Okay. Full stop. What is the final temperature of the mixture?
What is the
final temperature of the mixture? এটাকে এ দাও 1 এর এ দাও এটা তারপর বি নাম্বার লেখো state the assumption used for the process of calculation. State the assumption used for the process of calculation. Acha. B number 2. $1.3 kg of water at 20 degrees Celsius is mixed with 250 grams of ice at -5 degrees Celsius. $250 of ice at -5 degrees Celsius. Full stop. Find out the final condition of the mixture. Find out the final condition of the mixture. আচ্ছা নাম্বার 3 তে লেখো 2 kg of water at 10 degrees Celsius is mixed with 1.5 kg of ice at 0 degrees Celsius.
Sir, could you repeat the first part?
2 kg of water at 10 degrees Celsius is mixed with ice কতটুকু বলছিলাম জানো 1.5 kg ice at 0 degrees Celsius. Find the final condition of the mixture. কোশ্চেন গুলো এখানে শেষ। নিচে আরেকটা প্যারাগ্রাফে একটা ব্র্যাকেট দাও, ব্র্যাকেট দিয়ে লিখো condition in these cases mean condition in these cases mean condition in these cases mean composition of the mixture. Composition of the mixture dash how much water and how much ice comma and also the final temperature of the mixture. Okay?
Yes, sir.
আচ্ছা, যে কোনো একজন একটু পড়ে শোনাও।
Top to bottom?
হ্যাঁ, আস্তে আস্তে পড়ো, সবাই একটু মিলে দেখো যে নাম্বারগুলো ঠিক লিখছো কিনা। শুরুতে পড়ে যাও।
Okay, sir. Specific heat capacity of water CW equals to 4.2 into 10 to the power 3 joule per kilogram per Kelvin. Specific heat capacity of ice CI equals 2.1 into 10 to the power 3 joule per kilogram per Kelvin. Specific heat capacity of steam CS equals to 1.2 into 10 to the power 3 joule per kilogram per Kelvin. Specific latent heat of melting of ice equals 3.4 into 10 to the power 5 joule per kilogram, which is given as LF. Specific latent heat of vaporization of water LV equals 2.3 into 10 to the power 6 joule per kilogram. 1A. 2 kilogram water at 10 degrees Celsius is mixed with 4.3 kilograms of water at 62 degrees Celsius. What is the final temperature of the mixture? 1B. State the assumption used for the process of calculation. 2. 1.3 kilograms of water at 20 degrees Celsius is mixed with 250 grams of ice at 5 degrees Celsius. Find out the final condition of the mixture. 3. 2 kilograms of water at 10 degrees Celsius is mixed with 1.5 kilograms of ice at 0 degrees Celsius. Find the final condition of the mixture. Condition in these cases mean composition of the mixture. how much water and how much ice, and also the final temperature of the mixture.
ঠিক আছে
স্যার একটা 2 এ টেম্পারেচারটা কত?
-5 -5
2 এর টেম্পারেচার গুলো একটু বলো আমার মুখস্থ নাই
2 তে হচ্ছে 1.3 kilograms of water at 20 degrees Celsius is mixed with 250 grams of ice at -5 degrees Celsius.
ঠিক আছে আচ্ছা তোমরা বুদ্ধি খাটায় যদি বই দরকার বই থেকে হেল্প নিয়ে যদি সময় পাও এই কোশ্চেনগুলো ট্রাই করবা সবগুলো হয়তো নাও পারতে পারো ডিফারেন্ট পাবলিকে ডিফারেন্ট আনসার আসতে পারে if you want to collab with someone you message those people work in groups but that's your headache but try to come up with some numbers for the solution of these questions and we'll start discussing about these problems from next class yes sir
সেটা মানে অলওয়েজ দিছিলেন
অলওয়েজ
স্যার একবার দিছিলেন এরকম কিছু একটা
অলওয়েজ এর থেকে easiest problem ছিল now we're going to deal with something a bit more detailed yes sir
जी sir
Okay, sir.
Quran, thank you very much for your patience and all the best.
Assalamualaikum, sir.
Assalamualaikum. Allah best.
Assalamualaikum, sir.
Assalamualaikum.